more example in fracture mechanics, and this is going to be problem 584, at least that was the problem number used in the 10th edition. We might be in a different numbering in the 11th edition. But we have a plate that's 100 millimeters wide, 200 millimeters long, and 12 millimeters thick. And it's loaded in tension in the direction of the length right there. So that's what they're talking about down here. The plate contains a crack as shown here in this figure with the crack length of 16 millimeters. And the material has steel with a stress intensity, critical stress intensity of 80 megapascal square meters and a yield strength of 950. We want to determine the maximum possible load that can be applied before the plate yields and that or has uncontrolled crack growth. So there we go. So we're going to ignore stress concentration in part A, right? So we're basically just going to say, when does this thing fail? Well, what we have is we have material left right there, and we're also going to ignore bending too. That's another important aspect of this. We're going to ignore the fact that like this thing could, once you can picture that cracking, and the thing could actually start bending because there's a moment that's going to be offset in there. So let's see how I'm going to say this. I would say that stress is going to be equal to F over A, right? And critically, it's going to happen, this will occur when it equals yield strength, right? That's where in part A. So we want to find this yield force is going to be yield strength times the area. Now the area should be this stuff that's left over. So what they've told us is in this B, according to this, is going to be 100 millimeters, about 4 inches. Also going to notice that H is going to be also equal to 100 millimeters, right? Because they said this thing was 200 millimeters long right here. So that's how far that crack is from each side onto the thing. And they also said that the crack was 16 millimeters. So if we have the yield strength of 950, and we'll go, this is E to the 6 right there, right? And the area that's going to be left over is going to be first the thickness, right? The thickness is 12 millimeters thick, so T is equal to 12 millimeters. So we're going to have the thickness 0.012 times what's left over right here, which is going to be B minus A, right? So we'll say 0.1 minus our 0.016. I think I got that right. And so what we end up finding is we get 9.576 e to the 5, which is another way of saying 958 kilonewtons is when this thing would yield, right? So that's the force that would be required onto the end to be able to make this thing yield. Now we want to go for the fracture mechanics right here. And first thing we're going to need to do is find our beta. And we're in this thing right here. So we need H over B, and we also need A over B. So H over B is going to be 100 divided by 100, and I think we could do that. That's 1. And then A over B is going to be 16 over 100. And I get 0.16 EV. Easy, easy, easy. So, looking up through this and moving this thing around, I guess, okay, I'm moving, I see what happened. Here's 1, and here's 0.16 right there. Right? Here's 0.1, here's 0.2, So halfway up is like right over there. It's like a little bit up higher. I say that this is going to be 1.3. All right, there's 1.5. We're going to call this 1.3. It's a beta. So beta is approximately 1.3. So we know that we're going to use the stress intensity, which is a calculation, this right here, square root of pi a, right here. So I know that when this equals the critical one, we're going to have failure. So we're going to need to find what that stress, we're going to find what the force is going to be right here. And, something I did before, I don't have enough room right here, but this right here is 1.008 e to the minus 3 meters squared, right? So that might be useful to us. And we know that the stress is going to be equal to F over A, right here. So that's the stress that we're going to be playing into the thing. So we set this to the critical one, which is 80. And you got to be careful with our units. And our units will be megapascals square meters. We're going to be okay with this square meters thing because we're going to use meters inside here. So I'm going to say 80 e to the 6 is going to be equal to beta of 1.3, and then we're going to have F over 1.008 e minus 3 square root of pi, and then 0.016. I do all that right? If I do all of that, I get an F for maybe, I could have called this one yield up here. And here it could be fracture, right? If I do, so this is going to be my F right in there. And I get 277 kilonewtons. Right, so there's a substantially different right here. So you could see that, and we could say that this one right here is actually 29% of the yield, right? 20%. So definitely will fail at a much lower force level. And there you go. That's your introduction to fracture mechanics. Not terribly exciting, but it is something that you know about now. It is a failure mode, or a study of failing that is important. And it's another example of our apples to apples kind of theme. So here you go.